All right, so for number 17, it says determine if the relation defines y as a function of x with a bunch of different things. And so the fundamentals of this is really making sure we don't have x values that are repeating, right? Because then it wouldn't be a function. So if we look at part A, we're given a bunch of ordered pairs. So we're given, let's see, we have -10, 4, -2, 2, 6, 0, and 14, -2. All right, so you can see that all 4 of those x values are different, right? So that means this can be a function. And so I'm just going to write yes, because it does define y as a function of x. And then if we go to part B, we see, okay, so if I write these out as an ordered pair, that would be, the first one would be 2, 13. And then we'd have 3, 25. And then 4, 25. And so even though the y values are repeating, the x values are not. And so, yes, this does define y as a function of x. Now, from part C, we can see that if we do like the vertical line test here, it goes through a bunch of different y's for the same x. And so that cannot be y, or cannot define y as a function of x, right? So then we're just going to say no. Okay, so for number 18, it says determine if the function is one-to-one, give an explanation supporting your choice. All right, so we're given the first one, says k of x is equal to x cubed plus 8. So if I were to kind of graph that out, let's kind of draw it here. We have, it's going to be kind of like a, it's kind of a cubic, kind of like that, right? And so we can see here that there is, for every x value, there is only one y value, right? Or there's only, one y value for each x value. And so we can say, yes, each x pairs with one y, each x goes with one y, and each y pairs with one x. Okay? Now, if we go to part B and we try and draw that out, I'm going to do it on the same thing over here. So we have x squared minus 6, so that's going to kind of look like this, right? And so if we see here, we see that the y value repeats. Like if we come to this y value, we see that there's another x value that gives us that same y value. So it is not going to be a one-to-one. So we'll say no, because a y value pairs with more than one x value. And then if we go to part 18, we can see, and this is a graph, right? So then we can perform the horizontal line test, and we see that this passes through the same y value for multiple x values, right? So then we just say no, does not pass horizontal line test. Total line test. All right, so for number 19, it says use composition of functions to determine if the two functions are inverses. Show all work. Okay, so we know that if these functions are inverses of each other, then that means f of g is going to equal x, and g of f is going to equal x. And then vice versa for the r of s and s of r, right? So we're going to do just that. We're going to take the compositions and see if they equal x. And if they equal x, then they'll be inverses. So let's start off with our f of g. So if we do f of g, that's going to equal 4 over x plus 4 over x minus 1 right? We just insert that g in there. And then we can find a common denominator on the bottom. So this is going to be 4. That's just going to be left alone for right now. That's going to be over. So then if we do a common denominator with this, that'll be x plus 4 minus x all over x. All right. And then we see that these x's cancel out, right? So then we're just left with 4 over x, right? And so then we can take the reciprocal of this, the 4 over x, and then multiply them together. So that's going to be equal to 4 times x over 4, which cancels those out and leaves us with x. So that's a good sign. And then if I come over to, let's see, well, if I just stay over here, let's stay over here. So then that's going to be g of f is going to equal, well, so that's going to leave us with 4 plus, and then 4 over x minus 1 over 4 over x minus 1, right? And so then we can find a common denominator up at top, and so that's going to be 4x minus 4 plus 4 over x minus 1, and then that whole thing is going to be over 4 over x minus 1, right? Okay, and so then we can, these 4's can kind of cancel each other out to 0, right? And so then we're just left with, and if we take the reciprocal of this and multiply it together, that's going to be 4x over x minus 1 times x minus 1 over 4. Well, let's see. So we have the x minus 1's that cancel, and then we have a 4's that cancel, and just leave us with x. And so I'm going to come over here, point over here, and say, yes, they are inverses of each other. Now, if we go to part B and try and find the composition of that, if we do R of S, that's going to equal, let's see, we'll have a negative 2 plus 6x minus 2 over 6, okay? And then that can be simplified to, okay, so the negative 2's can be combined to give us negative 4 plus 6x over 6. And we know that that's not going to give us x, right? That 4 and 6 don't cancel out to give us anything. We still have those there. And so we know that this does not equal x. And so we already know that the functions aren't going to be inverses, but just for good measure, we can do our s of r. And so if we do s of r, that's going to equal 6 times a negative 2 plus x over 6 minus 2, right? So then we can cancel those 6's out, and then we're left with negative 2 plus x plus negative 2. And so I'm going to erase that real quick. I'm just going to combine those negative 2's that we'll have, and that's going to give us negative 4 plus x, which does not equal x. And so we know that the answer to this one is going to be no. Okay, so for number 20, it says each function is a one-to-one function. Find the inverse and give your answer in inverse function notation. Okay, so if we go right here, these are the actual functions that we have. And so if we kind of set this up and we say, I'm just going to write this over here. F of x is equal to, let's just say y, all right? And so then we can kind of, to start finding the inverse process, we can say that x is equal to, and kind of just switch them around, say it's going to be equal to the cube root of 2y minus 5. And then we can just solve for y from there, or for our inverse, right? And so then, to get rid of that cube root, we can cube both sides. So then we're going to have x cubed is equal to 2y minus 5. And so then we can add that 5 on both sides. So then we'll get x cubed plus 5 is equal to 2y. And then we can just divide by 2. And so then we're just left with y is equal to x cubed plus 5 over 2, which is equal to our inverse of x, right? And so our final answer is just going to be f inverse of x is equal to x cubed plus 5 over 2. And so then, if we do part B, we can kind of do a similar process, right? So we're going to say x is equal to y minus 4 over y plus 2. Now what we can do with this, since we have a y in the denominator, we can just multiply this whole denominator over here. And so then we're going to get x times y plus 2 is equal to y minus 4. And then we can distribute that x to the y and to the 2. And so then that's going to give us xy plus 2x is equal to y minus 4. And now we're wanting to solve for y, right? So we want to get y on both sides. So what I'm going to do is I'm just going to subtract this y over here. And I'm also going to, actually, no, I'll just subtract the y over there first. And so then we'll have xy minus y plus 2x is equal to negative 4, right? And then I can subtract the 2x to the right side. And so then that's going to be xy minus y is equal to negative 4 minus 2x. And then I can factor out a y on this left side. So if I factor that out, that's going to be y times x minus 1 is equal to negative 4 minus 2x. And then I can divide by the x minus 1. And so then we'll get y is equal to, and that's going to be inverse of x, f inverse of x. And that's going to be equal to our actual function, which is negative 4 minus 2x over x minus 1. All right, so on number 21, we're asked to evaluate the function f of x equals 6 to the x at the given values of x. And then we can round to 4 decimal places if we need to. All right, so for part A, f of negative 3, so if we're to evaluate that, that's going to be equal to 6 to the negative 3rd power, right? So we can just plug that into our calculators. And let's see, whenever I plug it in, I get 0.0046 to 4 decimal places. And then for f of 3.8, that's going to be equal to 6 to the 3.8 power, which, let's see, I get 905.6799. Then if we do f of radical 13, that's going to be equal to 6 to the radical 13, right? And so then that's going to be equal to 639.2404. And then f of pi is going to be equal to 6 to the pi, which is just going to give us 278.37776. All right, so number 22, we are to graph the exponential function f of x is equal to 4 to the x. And it wants us to use a table to find points to plot. Okay, and then we find the domain and range. So if we create a table here, I'll just do it right here. And let's do 5 points. So this is going to be our x. And then we'll have our function. So that's going to be just 4 to the x, right? Or our y's. And so let's do, let's start at negative 2. And then we can go to negative 1. And then do 0 and 1 and 2. We can just go that far. And so then if we plug in these points, let's see. So 4 to the negative 2, that's going to be 1/16, right? And then if we do negative 1, that's going to be 1/4. And then 4 to the 0 is just going to be 1. And then 4 to the first is just going to give us 4. And then 4 to the second power is going to give us 16. And so we have a bunch of different values that we can work with, right? And plot. So then if we try and plot this, let's see, I'll just try to come over here. All right, so I'm just going to start at 0. And then if we have like, let's see, we'll have, oh, this is going to be -1, -2, we'll have 0, we'll have 1, and we'll have 2. Now this isn't going to really be to scale, but if we do like, if we make this like 1, 2, 3, 4, 5, 6, oh, my bad. Yeah, so if we try and kind of make it a little to scale, so we know that 0 is going to be at 1, so it's going to be right here. 1 is going to be at 4, and then 2 is going to be like way up here, right? Somewhere that we don't know. And then -1 is going to be at like a 4th, so that's going to be kind of down here. And then 2 is going to be even lower, or sorry, -2 is going to be even lower than that, so like down here, right? And so then if we try and graph this and kind of connect these points together, we'll see that it kind of makes it a little exponential like that. So if we're to write the domain and range of this function, so let's see, well, our x's can be anything, right? And so I'm just going to say domain is going to be from -infinity to infinity. It can be whatever. Now for a range, we're a little bit more limited, right? We can't go negative with an exponential function, with this exponential function. So let's see, when it's going left, it's approaching 0. It's never going to hit. So we can say it just is approaching 0, and then you can see it keeps increasing as the x values increase, so it's going from 0 to infinity. Okay, so for number 23, it says given the graph of f of x is equal to 1/2 to the x, graph g of x equals 1/2 to the x minus 3 plus 2. Now we state the shifts in the parent function f to the given function g. Okay, so first let's start out with naming our shifts. So let's see, if we got this -3 that's being applied to the x. Now if we remember how shifts work, we know that this means that it shifts 3 units right, and let's see, well then we have this plus 2 being applied to the whole function itself, so it also shifts 2 units up. Now if we plug in a point like, let's say g of 0, just so we know where that where one of the points on the graph is going to be, we get g of 0 is equal to 1/2 to the -3 plus 2, which if we put that in a calculator, it's going to give us like 10. So we know one of the points on this graph, and it's going to kind of be up at the top here. And we also know, now this is really important, with the horizontal asymptote, for the parent function, for this 1/2 to the x, it's at 0, right? But our entire function is shifting up too. So that means our horizontal asymptote is going to shift up too as well. And so we're going to have this like, let's see, let's shift up 2 right here. So I'm just going to draw that line, kind of like that. And so then, now that we have this point and we have our horizontal asymptote, we can kind of draw it in a similar kind of model. So it like models our parent function. This isn't the greatest, but you know where I'm trying to get at. And so, and this is going to be our new function, our new g of x function. All right, so for number 24, we have Kara needs to borrow $15,000, and then she has these 3 options to choose from. She has 5.5% simple interest for 4 years, 5.25 interest compounded monthly for 4 years, and then 5% interest compounded continuously for 4 years. Okay, and part A asks, how much total interest would Susan pay for each option? So if we go with option 1, I'll just say like, and I'm going to write it over here, 5.5% simple interest. That's our simple interest. So that's just going to be, our interest is going to be equal to the principal times the rate times the time, right? So in this case, it's going to be 15,000 times 0.055 times the time of 4 years, which gives 3,300 in interest. Now if we do 5.25% interest compounded monthly, we know that, okay, so the interest is going to equal, so we have our principal amount times 1 plus our rate over the number of times it's compounded in a year. So if we have monthly, so that means, well, there are 12 months in a year, right? So this is going to be R over 12 to the, well, number of times it's compounded in a year. So this is going to be 12t, and then minus our principal amount, because this gives us like our amount at the end, right? Our total amount that we get. So we need to subtract that 15,000 off to see how much interest we made off of it. And so that's going to be equal to 15,000 times 1 plus 0.0525, it's getting kind of cramped here, over 12 to the 12 times 4. Oh, you can't see that. Okay. But it's going to be to the 12. Oh, my goodness gracious. There we go. I want that. Kind of get rid of this. To the, you know what? I'm just going to do it down here. 15,000 to the 1 plus 0.0525 over 12 to the 12 times 4, and then minus 15,000. And then if you plug all those numbers in, I think you should get 3,496.70 cents. All right, and so then if we do 5% continuously, that's going to be our interest is equal to, so we got principal times e to the RT, right? And then minus our principal yet again, because the P times e to the RT gives us the total amount at the end, and we want just the interest. And so let's see, that's going to be equal to 15,000 times e to the 0.05 times t, which is 4, minus 15,000. And so then if we do that, we will get something, let me see. Okay, so I think that's going to be 3,321. And I'm going to do dollars, yeah. 321.04. So that is part A. So for part B, it asks which option would be best for Susan, assuming she wants to pay the least amount of interest possible. Okay, so if we look, we have 3,300, 3,321, and 3,496. Now, out of all of these, the simple interest is the least amount, right? So we can just say 5.5% is the best. 5.5% simple interest, right? I'll specify that. 5.5% simple interest is the best option. Okay, so for number 25, we have, it says a veterinarian depreciates a $10,000 x-ray machine. He estimates that the resale value after T years is 90% of its value from the previous year, and then it gives us the equation for us, which is really nice. And so for part A, it asks to find the resale value after 4 years. So we're going to use this resale value formula, and that's just going to be V of 4, which is going to be 10,000 times 0.9 to the 4, which gives about 6,561. Now in part B, it says if the veterinarian wants to sell his practice 8 years after the x-ray machine was purchased, how much is the machine worth? And then it asks to round to the nearest 100, show all work. Okay, so the resale value, because that's, I mean, the resale value is how much the X-ray machine is going to be worth. Well, we're wanting to find basically V of 8, right? If he wants to sell 8 years after the X-ray was purchased. So that's going to be 10,000 times 0.9 to the 8, which gives 4304.67, but it asks around to the nearest 100. So this is going to be about $4,300. Okay, so for number 26, it asks to write all of these logarithmic equations in exponential form. And so for this first one, we look at what the log base is. So it looks like it has a base of 5, right? So in order to get rid of that log base, we're just going to take 5 to each side, right? And so then we're left with 5 cubed, 5 to the third, is equal to 125, whatever was left in that log. So that's our first one. And then for part B, we have natural log of x plus 4 is equal to 3. And so basically what we're going to do is we're going to take each side to the e power, right? So we're going to have that. And then we're just going to be left with, e cubed is equal to x plus 4. So that's the exponential form of that one. And then for this last one, it gives variables, so it's trying to trip us up here. But we know that we can take both sides to the base, and the base in this case is k. So then we're going to take both sides k to that power. So then we're going to have, let's see, we're going to have r, because that's all that's left on the inside, is equal to k to the m. All right, so in a similar way, on number 27, it wants us to write the exponential equations in logarithmic form. And so we know that what we're going to have to do is take, in part A, take both sides to the thing that has an exponent that's being taken to an exponent. And so in this case, it's 2. So we're going to have to take both sides to a log base 2. So if we take this to a log base 2, that's going to get rid of the 2's. And so we're left with, and we're going to have to take this to a log base 2 as well, right? So then we're just left with 4 is equal to log base 2 of 16. So that's our first one. Now going on to our second one, we have a 1/2 that's being taken to a negative 5th power. So we're going to take both sides to a log base 1/5, or sorry, not log base 1/5, log base 1/2, log base 1/2. And so then we're left with negative 5 is equal to log base 1/2 of 32. And then for this last one, we have 8 to the 9th is equal to b. So then we're going to take both sides to a log base a, right, to get that out of that exponent out of there. We just don't want anything in the exponent, basically. And so then we're left with 9 is equal to log base a, sorry, my g's, my 9's, my a's, they all look the same. But that's going to be log base a of b. So then that's going to be our answer for that one. And then I forgot to box this up here, but that's going to be our answer for that one. Okay, so for number 28, we have to evaluate the following logarithmic expressions without a calculator, and we have to show our work for that. And so basically we have this, so for part A, we have this log base 2 of 64, and that's going to be equal to some x value that we don't know, that we're trying to solve for, right? So what I'm going to do is I'm going to take both sides to those powers. So then we're going to have, this cancels out the 2 log base 2, so then we're left with 64 is equal to 2 to the x, right? And so now I have to think about, okay, what value, whenever I take 2 to a value, what value is that gives me 64? And so if I remember correctly, if we take 2 to the 6th power, that gives us 64. And so in this case, that gives us x equals 64, or sorry, x equals 6. And so then we can say log base 2 of 64 is equal to 6. And so if I do that for the similar thing down here, I take 3 to this power, and so that's going to be in 3 to the x, right? So then we have, cancels out the 3 and the log base 3. So then we're left with 1/9 is equal to 3 to some x power. Okay, so what power, when I take 3 to that specific power, gives me 1/9? If I remember correctly, well, this 9th is in the denominator, right? So we know we're going to have a negative, it be to a negative power. And we know that 3 squared is 9. And so that means that x has to be -2. Or if I rewrite this again, log base 3 of 1/9 is equal to -2. And then for this last one, if we come down here, that's going to be, well, just the log. That means it's going to be a log base 10, right? So then I'm going to take both sides. I'm going to take 10 to both sides. So then that's going to cancel out the 10 and the log base 10. So then we're going to have 10,000 is equal to 10 to the x. Now, if I think about what value, whenever I take 10 to that value, gives me 10,000, I think that's 4. So we're going to have, yeah, so it's going to be x is equal to 4 in this case. Or we'll just say log of 10,000, 10, I think you're right, yeah, 10,000 is equal to 4. Okay, so for number 29, we have to simplify the following expressions. So let's start with part A. So we have 2 to the log base 2 of x minus y. And so we know that whenever we take 2 to the log of its base, or sorry, we take a value to the log of its base of the same value, we're just left with the inside of that log. And so this 2 and this log base 2 cancel out, and giving us a simplified expression of x minus y. Now, in a similar way here, this is kind of the reverse on part B, right? We got log base 7 of 7 to the 13th. And so this log base 7 and this 7 cancel out, and so we're just left with the exponent, which gives us 13. And so then, now we know that the natural log and e, they're opposites of each other, and so they're going to cancel each other out, and we're just left with the exponent once again, and so that's just going to be x squared plus 2. And now, this one's a little bit trickier, but log base p of p, so I mean, if we think about, I don't know, like us up here on part B, we did log base 7 of 7, which kind of canceled out, the log base 7 and 7 kind of canceled out to give us essentially just 1, right? And so then we were just left with 13. Well, in the same way here, log base p of p, they're going to cancel each other out and then just give us 1. And then if we evaluate the natural log of 1, we know that that's just going to be 0. Okay, so on number 30, we have to identify the shifts from the graph of the parent function f of x is equal to log base 2 of x to the graph of the related function g of x is equal to log base 2 of x plus 5 minus 2. Okay, so we can see that we have this plus 5 being kind of, applied to this x here, just in that x, in that log. So we know that the g of x is going to shift left 5 units, and then we have a -2 that's being applied on the outside, so it's also going to shift down 2 units. All right, so on number 31, we have to apply product, quotient, and power properties of logarithms and simplify if possible. All right, so I'm just going to start off with part A. So we have log base 4 of the 7th root of x to the 5th, which I don't know about you, but that's looking a little complicated to me. So let's take this x to the 5th, or sorry, this 7th root of x to the 5th, and see if we can write it in just like exponential form. So this root 7 can be rewritten inside a fraction, right? So then we're just going to have x to the 5 over 7, so x to the 5/7, which gives us log base 4 of x to the 5/7. And we know that if we have x, something to an exponent in a log, then we can take that exponent and we can bring it out here and multiply it by the log, right? So our simplified version of this is going to be 5/7 times log base 4 of x. All right, so then if we go to this one, we have m squared plus n over 100. So remember that if we have something being divided or multiplied in log, there are specific rules that apply to it, right? So this m squared plus n is being divided by 100. So what we can do is we can say that this is like log of m squared plus n minus, remember, because it's being divided, log of 100. And that log of 100 can actually simplify down even more. And so then we're left with log of m squared plus n minus 2, if you put that in your calculator. All right, so then we come down to this last one. And let's see, so can we simplify this some more? Let's take a look at it. So first, I see that we have this log base 7 of 49 times k. Now, in a similar way that we did in part B, these are being multiplied, right? So instead of having this log minus log, we're going to have log base 7 of 49 plus log base 7 of k, right? And this log base 7 of 49 actually simplifies further too, and so we're left with 2 plus log base 7 of k. All right, so on number 32, we have to write the logarithm as a sum or difference of logarithms, and we have to simplify each term. So yeah, right now it looks kind of daunting, right? So let's try and simplify this as best we can. So we have this, I'm just going to rewrite this. I see a radical and I want to rewrite that immediately. And so this can be rewritten as natural log of, and then I'm going to put in parentheses, x squared plus 4 over e to the third to the 1/4 power, right? And so this 1/4, now that it's being taken to a power, can be brought outside in front of the log, right? Or in front of the natural log. So then it's going to be 1/4 times natural log of x squared plus 4 over e to the third, right? And so then, now I see that we have an e to the third in the denominator, and we know that when something is being divided in natural log, we can take it out and like subtract it in its own little natural log. And so this is going to be equal to 1/4 times the whole thing of natural log of x squared plus 4 minus natural log of e to the negative, or sorry, e to the, not e to the negative third, but just e to the third, right? Kind of got carried away with my negatives there. There we go. And so then we can, well, we see that the natural log and e, they cancel each other out, right? And just leave us with 3. And so then if we simplify this even further and we distribute this 1/4 to this first one and this second term, we're left with 1/4 times natural log of x squared plus 4, and then minus, remember I said that natural log and e canceled out to give us 3, and then if we're multiplying that 3 by 1/4, that's just going to be minus 3 over 4. So that's our simplified expression. Now on number 33, we have to write the logarithmic expression as a single logarithm with coefficient of 1. Okay, so first let's take a look at these two terms. Let's just take it a term at a time. So we are given, actually, let's just take one term at a time, just like I said. So we take a look at this term first and see if we can simplify it any. So I see we got a 4 in front of that log base 6 of r. So what we can do is we can bring that inside the log. So then we're going to have log base 6 of r to the 4th, right? And then let's see, minus, all right, so this 3 log base 6 of s. So a similar thing can happen here, right? We got to take that 3 inside the natural log and take it to the exponent. So then we're going to have minus log base 6 of s cubed. And then this last term is going to be minus, and then we got this 2, and so we're just going to bring that in there and say that's going to be minus log base 6 of t squared. And so then we can go about combining these terms, right? And so we have this log base 6 minus log base 6 of r to the 4th minus log base 6 of s cubed. So we know that when logs are being subtracted, that the one being subtracted can go in the denominator as a single log. So that's going to be like log base 6 of r to the 4th over log base 6. So then that's going to be over s cubed, right? And it's also subtracting a log base 6 of t squared. And so then that t squared is going to go in the denominator as well. And so when all is said and done, this is our simplified logarithmic expression. It's going to be log base 6 of r to the 4th divided by s cubed times t squared.